Okay, May, June 2022, paper 3, variant 1. Question 1. Figure 1.1 shows a dripping tap with a measuring cylinder. The student collects 200 of the drops in the measuring cylinder. The total volume collected is 60 centimeters cubed. Calculate the average volume of one drop of this water. How can I find the average volume? Okay, you need to divide. You need to divide the total volume by the number of drops. So basically 60 divided by 200, total volume, 60 divided by 200. So the average volume of one drop would be 0.3 centimeters cubed. The average volume would be 0.3 centimeters cubed. Another student uses a stopwatch to measure the time taken for the tap to produce 200 drops. Okay. Determine the time in seconds. Can I find the time in seconds? Yes, the time in seconds is 3 minutes. So just multiply 3 times 60, which is 180 plus 46.5. 180 plus 46.5 is 226.5. Okay, 226.5. Yeah. Next question. Can I find the time interval between two drops? Can I find the time interval for one drop to fall? Yes, I can find the time interval. All you need to do is divide the total time by the number of drops. Okay, total time by the number of drops. So 226 divided by 200, 226.5 divided by 200 would give you roughly 1.1. Okay, roughly 1.1 seconds. This is the time interval for one drop. Figure 1.3 shows the volume of water. What is the volume of water in this? The time interval means the time taken for one drop to fall. This is what they mean by time interval. Okay. Why didn't I divide by 60? Because you need to divide by the number of drops, not by the volume. You need to divide by the number of drops. Okay, can I find the volume, or can I take the reading of this volume? Yes, the reading of this volume. When we take the reading of the volume from the measuring cylinder, we always take the reading from the bottom of the meniscus. So the reading from the bottom of the meniscus would be 84, not 83. It would be 84 centimeters cubed. 84. Okay, from the bottom of the meniscus. Each one of these is 2 centimeters cubed. Figure 2.1 shows the speed time graph for two cars, A and B. Determine the speed of car A at 10 seconds. Car A at 10 seconds. So at 10 seconds, where's 10 seconds? You need to draw a line, okay, until you reach car A. At this point, the speed was 9.3. Okay, 9.3. If you zoom in, you'd find that it's in the center of the square. It's in the middle. This is 9, okay? And this is 9.2. So it's just above 9.2 and just below 9.4. So it should be 9.3 meters per second. 9.3 meters per second. 9.2 would be wrong. There is no range for this question. For this question, there is no range. Okay, 9.2 would be wrong. This question is 9.3 exactly. You need to draw a very thin line. Make sure that the line is exactly reaching the line and it's exactly in the center of the square. You need to be very accurate while finding the reading. Okay? No, it's not on the square exactly. It's in the center. State and explain which car has the greater acceleration during the first 10 seconds, A or B. I guess it would be A. Definitely, it is A. Why is it A? Because it has a steeper slope. It's A because it has a steeper slope. Steeper slope or steeper gradient. Question B. Describe the motion of the car after 30 seconds. Car B after 30 seconds. Where's car B after 30 seconds? How is it moving? It's moving with a constant speed. moving with a constant speed. But since it's 2 marks, you need to actually state the speed. You need to state the speed. The speed of the car would be 16 meters per second. So it's moving with a constant speed of 16 meters per second. Constant speed of 16 meters per second. Can I find the distance moved by car brief from 0 to 30? Yes, I can find the car distance from 0 to 30. Distance is area under the graph all the way up to 30, okay, which is half times base times height. Half times base times distance equals half times, distance is area under the graph. You need to write it down, area under the graph, which is half times 30 times 16. So 8 times 16 is 240 meters. Okay. And question 3, calculate the area of the metal block in contact with the ground. The area in contact with the ground is 2 times what? 2 times 12. So 2 times 12 is 24 centimeters cubed. Okay. 24 centimeters cubed. The mass of the block is 0.84 kilograms. Can I find the weight of the block? Yes, weight equals mg. 0.84 times 9.8. I know this is an old test, but we can use 9.8, okay, which is around 8.4 or 8.3, okay. Okay, 0.84 times 9.8 would be around 8.2 actually. Sorry, 8.2 newtons. For the area, okay, the area, you need the area in contact with the ground. I'm not asking about the surface area of the block or whatever. I'm asking about the area in contact with the ground. The ground is 2 and this side is 12. So 2 times 12 is 24 centimeters squared. A different metal block has a weight of 24. The area in contact with the ground is 4 centimeters cubed. Can I find the pressure? Yes, pressure equals force over area. Force is 24, which is the weight and the area in contact with this other block. It's a different block. 24 divided by 4 is 6 newtons per centimeter squared. It's a very easy answer. Okay, figure 4.1 shows an electric, yes, 24 divided by 4. Shows an electric motor and pulley. It was 24 divided by 4, so it's 6, yes. Um, and the pulley being used to raise the load M. The electric motor uses the belt, okay, to pull the pulley. With when the electric motor lifts the load, energy is transferred. Electrical energy. We have two types of energy transfers: useful and wasted energy. Useful energy and wasted energy. What are the two types of useful energy transfers in this question? And what is the wasted energy in this question? Useful energy could be hmm, useful energy could be gravitation because it's being pulled up, and kinetic. Yes, and kinetic. What about the wasted energy? We always say that the wasted energy is what? Is kinetic energy and gravitational potential energy. Wasted energy is usually thermal energy. Okay, could be some of it could be sound, but mostly it is thermal energy. Mostly it is heat energy that is wasted due to the friction. Okay, due to the friction. Okay. Hmm. Can I find the moment? Elastic useful? No, it's not useful. Uh, can I find the moment? Moment equals force times perpendicular distance. Moment equals force times perpendicular distance from the pivot. So 2.5 times 20 is 50 Newton centimeters. Okay, 50 Newton centimeters. Yeah, moment. Describe how the wind turbine generates electricity from energy in the wind. Energy in the wind. What is the energy in the wind? What is the energy stored in the wind? Wind is moving What type of energy is in the wind? Wind has kinetic energy. So kinetic energy, okay, in the wind rotates the turbine, which also rotates what? Huh? Which rotates the generator, producing producing electrical energy. Apart from cost, state two advantages of generating electricity using wind turbines compared with using a power station that burns coal. Apart from cost, we need to find two advantages of generating electricity using wind turbines. You can say it's renewable. Can I say it's renewable? No pollution. Okay, no air pollution. You can say what else? Yes, no air pollution. It's renewable. But mainly we need to say these two things. So it's renewable and no air pollution. You might say no acid rain, no greenhouse effects, no contribution to the global warming and whatnot. Yes. Apart from costs, state two disadvantages of using generated electricity using wind turbines. Huh. Noisy, yes, okay. You could say it's noisy. You can say it's not reliable. Yes. Needs a large surface area. Yes, large surface area. Okay. It's not reliable. Visual pollution. Visual pollution is not wrong. Okay, it's not wrong, but you have many other more much better disadvantages. It's not wrong, but you have other better disadvantages. Okay, a teacher fills a copper can with with solid wax and heats the can. She measures the temperature of the wax every minute. She continues heating once the wax has melted and stops heating when the wax is boiling. State the term used for the process that transfers thermal energy through the copper. Through the copper. What is the main type of energy? Yes, it is conduction. Thank you. It is. Conduction. Excellent. In figure 6.1, the temperature of the wax changes as it's heated. Find the melting point, the boiling point, and the time at which the wax starts to boil. Melting, boiling, and the time at which the wax starts to boil. We need to first find the two temperatures. Melting point would be it would be, yes, at this temperature. What is this temperature? What is this temperature? So this is 50, uh, this is 75, and this would be 80. So at 80 degrees Celsius, it starts to melt. The boiling point, it's at this point. Okay, what is this point? Again, this is 150, so this is 175, this is 170, not okay, cannot be anything else. It's 170 exactly. Okay, this is 170. Find the time at which the wax starts to boil at this time. What is this time? So 20, 25, and 26 minutes exactly. 26 minutes. Question B. Describe the molecular structure of the wax in terms of the arrangement, separation, motion. We need to talk about everything. 6 marks. That's a lot. That is a lot. Okay, so we need to talk about arrangement, separation, and motion of each of the solid and the gas. What about the arrangement? Solid, they have a fixed arrangement. Okay. What about the separation? Very close together or touching? Very close together. What about the motion? Fixed. They vibrate in fixed place. Can I say regular arrangement? Yes, I can say regular arrangement. Okay. Vibrate in fixed place. What about the wax as a gas? Does it have a fixed arrangement? No, irregular arrangement. Irregular arrangement. Distances very far apart. Very far apart. What about the motion? Fast and random in all directions. Hmm. Okay. Yeah, that's easy. Yes, wax can be a gas, definitely, when it boils. Um, Figure 7.1 shows the displacement of particles in water wave. Can I find the wavelength of this wave? Can I find? Yes, I can find the wavelength of this wave. How can I find the wavelength? It's from 0 to, yes, it is 80. 8, I mean. It is 8. Yes, thank you. How is it 8? Because you completed the full wave. Okay? Half a cycle and then another half a cycle, which is 8 centimeters. Yes. Can I find the amplitude of this wave? Yes, the amplitude would be up to the crest. So it is 1.5 centimeters. Thank you. It is 1.5 centimeters. If you measure the distance from the crest to the crest, yes, it would give you 8. Yes, from the crest to crest. So this crest is at 6, and this other crest is at 14. So the distance is also 8. Again, exactly, it's correct. The water wave travels from deep to shallow. Can I complete 3 wavefronts in the shallow water? Okay. So as they move to the shallow water, what happens? You need to state what happens to speed. Speed decreases. What happens to the wavelength? Wavelength decreases and it bends towards the normal. Bends towards the normal. So at the boundary, they will bend towards the normal somewhat in this direction. Okay, so this is the bending of the wave. Okay, in this direction. Bending of the wave in this direction. Yep. So this means that the wave has bent. Okay, it has refracted. This is the process. Okay, refraction as it moves from deep to shallow. State the name of one type of electromagnetic wave with a wavelength shorter than that of visible light. Wavelength shorter than that of visible light. Visible light. So we have Rami. Looks great. We need a wavelength which is shorter. So either radio waves, microwaves, or infrared. Yes, radio, micro, or infrared. State one use of the type that you have given. For example, if I had said radio waves, you can say radio fly. Okay. You can say Bluetooth transmission. Infrared, if someone said infrared, okay, so infrared, we can say remote control. Remote control. Frequency and wavelength are inversely proportional in these waves. Yes, as you increase the frequency, the wavelength decreases. Exactly. Figure 8.1 shows a bar magnet and a piece of card. Describe an experiment to determine the pattern of the magnetic field lines around the magnet you may draw. How can I find the radio waves are in you can use radio fly, which is the radio device. Yeah. Ah, can I find the magnetic field or direction of the magnetic field around this bar magnet? Yes, using compasses. Using compasses. So basically, you need to place, okay, place the compass at different positions, different positions around the bar magnet. Okay, different positions around the bar magnet. At each position, yeah, at each position, draw an arrow. Draw an arrow with the direction, with the direction of the North Pole, or the arrowhead, or the compass head, needle head, okay, of the compass, draw the direction, draw an arrow with the direction of the north head of the compass, of the needle head, and then you can say just join the arrows using a line. Okay, join the arrows using a line. Okay, all you do is you use the compass. For example, if this was a North Pole and this was a South Pole, okay, this was a North Pole and this was a South Pole, the compass head would be directed this way, okay, to look this way, to look to the right, and here to look to the right. So basically, just draw an arrow. Okay, you draw an arrow this direction, draw an arrow in this direction, you draw an arrow in this direction. Meaning, okay, how can I join the lines? Okay, if you join the lines, you'd find it's going this way. Okay, you'd find it's going this way. Near the North Pole, it's moving outwards, and near the South Pole, it's moving inwards. Into the South Pole, out of the North Pole, from the North Pole to the South Pole, from the North to the South. Okay? Okay. Yeah. Student has a bar magnet and a metal bar with ends labeled X and Y. State and explain what these results reveal about the metal bar XY. X is attracted to the North Pole and then it is attracted to the South Pole. It's attracted to the North Pole and is attracted to the South Pole. Is this a magnet? Could this be a magnet? Could this be a magnet? I don't think so. It shouldn't be a magnet. This is an iron bar, isn't it? It is an iron bar. It's an unmagnetized metal. To be more specific, it's an unmagnetized piece of iron. It's an unmagnetized piece of iron. Why? Because it attracts from both ends. Attracts from the North Pole and the South Pole. So it's unmagnetized. Un unmagnetized iron bar. Why? Because it's attracted from both ends. Okay. Figure 9.1 shows an electric circuit which includes an uninsulated resistance wire XY, sliding contact, which is C. Okay, it's now located at point P. State and explain the effect of the ammeter reading when they move C from Y to X. As they move C from Y to X, it's moving this way. Okay, from Y to X. Yeah. What would happen as it moves from Y to X? As it's moving in this direction, would the resistance increase or decrease, or what happens to the resistance? Well, as it moves this way, does the resistance increase or decrease? It's getting shorter, isn't it? It's getting shorter. So the resistance is decreasing. Therefore, what happens to the current? He's asking about the ammeter reading. So the ammeter reading would increase. So we need to say that the resistance, okay? Resistance decreases and therefore the current increases. Current increases. Yeah. calculate the reading on the ammeter when contact C is at X. Contact C is at X. Calculate the reading. When it's at X, if you think about it, why does the resistance decrease? Because the length decreases. Because the length is decreasing. As you're moving from Y to X, the length is decreasing, and we know that the length is directly proportional to the resistance. So as it's moving towards X, and now the contact is exactly at X, so the contact has reached this point. The distance is zero, so the resistance is also zero. Can I find the reading on a meter? On the meter, yes, I can find the reading. Can I find the current? Yes, you have the resistance. Where's the resistance? You only have one resistor in this case. You only have one resistor in this case, which is the fixed resistor, the 8 ohm resistor. And then you have the voltage. Can you find the current? Yes, I equals V over R. I equals V over R, which is 6 over 8, so 0.75 amperes. 0.75 amperes. The students move contact C to point P. The resistance of the wire between X and P is 20 ohms. He moves it to P. Now, خلاص, instead of being at X, it's now at P. So the resistance of the wire is now 20 ohms. 20 ohms. Can I find the total resistance? Can I find the total resistance? I guess so. You have two resistors and they are in series. If you have resistors in series, what should you do to the total resistance? How can you find the combined resistance? You just add them up. So 20 plus 8 is 28 ohms. 28 ohms. Yeah. The electric current in the circuit produces two effects. Two effects. What are these two effects? Place a tick in the boxes next to these two effects. What are these two effects? Does anyone know what are these two effects? Two effects. Electric current. It creates a magnetic field. Yes, it does create a magnetic field. We said the magnetic field should be around the wire. Does it create a gravitational? No. Does it create a heating effect? A heating effect? Yes, it does. Yes. You said as the current increases, the temperature of the wire increases. Heating effect. It definitely doesn't create a sound or any X-ray emissions. A microwave oven. Okay, microwave oven has a metal case and is connected to a 240 volt electric supply. Okay, the microwave is fitted with a 13 ampere fuse and an earth wire. A fault occurs and the live wire on the microwave even oven touches the metal case. Explain how the fuse and the earth metal can protect the appliance and the user. So basically, we need to talk about the fuse and the earth wire. We can talk about the fuse and the earth wire. First of all, if you talk about the fuse, if we talk about the fuse, how does the fuse prevent, or how does the fuse keep us safe? It cuts off the circuit, or cuts off the current, okay? The fuse, okay, breaks the circuit, when the current increases above a certain amount. Above a certain amount. Now, we need to understand what is an earth wire. It's a very simple concept. What is an earth wire? Basically, if you have a metal case, This is a metal case. Such as what? Metal case. Such as the microwave oven, or a refrigerator, or a dishwashing machine, or whatever huge appliance, okay, that has electricity, obviously, and that has a metal case on the outside. These metal cases are good conductors of electricity. They have free moving electrons and they are good conductors of electricity. So basically, if there is a current in these cases, in these metal cases, if there is a current, if the live wire, okay, the positive end of of the wire, if it touches this metal case for any reason, Okay, I don't know what is the reason. For any reason, if the live wire touches the case and you touch the case at the same time, what happens? You'll get electrocuted. So an electric shock. So what does this earth wire do? What does this earth? It's literally a wire connected to the earth. It's literally a wire connected to the ground. Okay, it's a wire connected to the ground. If there are any free moving, if there are any excess electrons, any extra electrons, okay, due to the current, due to this live wire touching the metal case. Okay, the live wire is the positive end of the wire. So if you have a battery, for example, positive and negative, so the positive end is we can consider it to be the live wire. So if this live wire touches the metal case and you touch the metal case, you will be electrocuted. What does this earth wire do? Okay, what does this earth wire do? It is connected to the ground and it allows any excess electrons to pass to the earth. So all of the excess electrons, any extra electrons, okay, will pass to the earth. Okay, so the earth wire, okay, prevents prevents electric shock, prevents electric shock if the live wire, okay, if the live wire touches, okay, touches the metal case. How? Metal case. How does it do that? By allowing the electrons to flow to the earth. So if you have any excess electrons, if you have any extra electrons on the metal case, and if you touch the metal case with these excess electrons, you'll get electrocuted, an electric shock. So how can you prevent it? By just connecting this metal case, by connecting this device to the earth using a simple wire, a very simple wire. You'll connect this simple wire to the earth, and then all of these electrons will be discharged. All of these electrons will be discharged to the earth, preventing an electric shock. Yes, all of the electric appliances, especially those with high currents, such as the AC, such as the refrigerator, the dishwashing machine, the microwave oven, okay, they all have earth wires, okay? Can I find the secondary voltage? Can I find the secondary voltage? Yes, I can find the secondary voltage. Because you have the primary voltage, you have the number of turns on the primary coil, you have the number of turns on the secondary coil. So basically, Vp over Np equals a Vs over Ns. Vp, what is Vp? 240. Np is 70. Vs, I need to find Vs, but Ns is 560. 560. Cross multiply. By a very simple cross multiplication, it would be 240 times 560 divided by 70, which is 1920. 1920 volts. So this is VP. Hmm. VP. No. Last question. Question 11. A teacher determines the type of emission from a radioactive source. He uses different materials to absorb the emission. Okay, a radioactive source. Teacher places a material between the radioactive source and the detector. Material being tested. Um, he repeats the experiment. If you had no, if you had nothing between the object and the source, between the source and the detector, the count rate was 480. If you had the thin sheet of paper, it was 481. Aluminum 479, and 10 millimeter block of lead 120. Okay. Does it have any alpha or beta or gamma? We need to find out. State whether the source emits alpha radiation or alpha particles. Does it have any alpha particles? No. Uh, no alpha and no beta. He's not asking about beta, but yes, no alpha particles. Why no alpha No alpha particles. Why? Because if there were any alpha particles, if there were any alpha particles, the number should have increased. I'm sorry, should have decreased. Should have decreased. It should have even decreased significantly. It should have decreased significantly. So you can say that the number or the count rate didn't change. Didn't change. Okay? Should be less. Should be less than 480. Actually, for this question, if he asks you if there are any beta particles being produced, okay, if there are any beta particles being produced, you'd also say no. Why wouldn't you say no? Why would you say no? Because the number is almost the same. 479 is almost the same as 480. How does it change? 481, 479, they're not the same number. Numerically, they're not the same number, but experimentally, if you remember from paper 6, we always say we need to say whether it's within the range of experimental accuracy or not. Is it within the range? Definitely, it is within the range. How does it increase or decrease? Plus or minus 1, plus or minus 2. It could increase up to 5 or 6. It could increase some. How does it increase or decrease? Because of something called the background radiation. If you remember, you have the background radiation around us being produced by the rocks and being produced by the cosmic rays and the food and the trees and everything, literally everything around us produces background radiation. So the number could increase or decrease slightly, not significantly, slightly. Plus 1, minus 1, plus 2, minus 2. Okay. Um, Okay, state whether the source emits gamma radiation or not. When we added the lead block, did it decrease? Yes, definitely it did decrease. So yes, it does have, okay, yes, it does have gamma radiation. How did we know? Because the lead block, okay, the lead block has absorbed this gamma radiation, okay? It has absorbed this gamma radiation. Lead block absorbed the gamma, okay, radiation. طب if you ask what about the 120 counts per minute, the remaining 120 counts per minute, what is this? This is the background radiation. It is the background radiation. Okay,